Hello everyone. My name is Joel Dunham and I'm here to talk to you about LingSync, a web application for linguistic fieldwork. First off, I would like to thank the Department of Linguistics, Languages and Cultures here at the University of Calgary for inviting me to give this tutorial. What I want to do in the course of this tutorial is show you what LingSync is, why it was created, how you can use it right now, how we are planning to improve it, and then give you some hands-on practice using it. Here's the plan. The timings are just estimations. First, I'll give something of a traditional presentation on what LingSync is and what motivated its creation. Then I'll illustrate how to get started using LingSync right away for your linguistic fieldwork. Taking more as the operative word in the title of this workshop, I will then discuss the future of LingSync, describing the more interesting and exciting features that are planned and or under development. Finally, we'll use what we learned in the how-to section to try our hands at creating a corpus as a group. Please feel free to interrupt and ask me questions at any point during the tutorial. Here is the LingSync URL, which is the hub for all things LingSync related. And here is the official one-sentence description. LingSync is a free tool for creating and maintaining a shared database for communities, linguists, and language learners. Essentially, LingSync is linguistic fieldwork software that focuses on collaborative data creation and maintenance, and on making data accessible, shareable, and reusable. I would like to briefly introduce myself so you can get a sense of what my interests are and what my role is with respect to LingSync. I just finished my PhD at UBC, and my dissertation is a description of and argument for another collaborative linguistic fieldwork application, which I built and which is called the Online Linguistic Database, or OLD. A major part of the OLD is an application for creating morphological parsers. My dissertation described an experiment in creating morphological parsers for Blackfoot, a language that I have fieldwork and research experience with. I will talk briefly about the OLD parser creator and the Blackfoot parsers later on in the presentation. I am about to begin a postdoc with Concordia University. The departments of linguistics at Concordia and McGill and a small company called iLanguage are responsible for the development of LingSync. My job over the next year, and maybe beyond that, is to improve LingSync by adding the good parts of the OLD to it, in particular the morphological parser creator application. This has some consequences for the present tutorial. First, it means that some of the features that I'm going to show you are not yet available in the current production version of LingSync. However, it's important to note that the LingSync fieldwork application that I will be showing you is stable and is currently being used by numerous field linguists and field methods classes. Also, I am very excited about the opportunity to begin throwing myself full-time into developing and improving this application. I truly believe that by building on the collaborative and computational possibilities of LingSync, there are a number of exciting ways that we can improve the methodology of linguistic fieldwork and the endeavors that rely upon it. In pursuit of that, I'm looking forward to introducing you to this tool and getting your feedback, perhaps now, perhaps after you have become more familiar with it, for how you would like to see it improved. So, LingSync is software for linguistic fieldwork. We can define linguistic fieldwork as working with speakers to generate artifacts that encode knowledge of a particular language. And of course, endangered languages fieldwork is the same thing, except in this case there are very few speakers, there are very little data, and as a result there is a real urgency. Now I realize that some in the audience might not be working on languages that would be considered endangered or even underdocumented. LingSync can still be useful to linguists working on those languages. However, the urgency of the endangered languages context was a key factor that led to the creation of LingSync, which is why I am discussing it here. So why do we do it? First, there is a general consensus that documenting and preserving linguistic diversity is important. We have a good idea of the kinds of things that we lose when we lose a language: histories, aspects of culture, scientific knowledge, ways of thinking. And most of us don't want to see these things lost forever. Second, there is a strong desire to see people learning and speaking these languages again. A lot of fieldwork effort is directed towards building resources that can help with teaching and learning these languages. Even when a language is sleeping, that is, when there are no more fluent speakers, it is still possible that by using the records generated through fieldwork, we can revive or awaken that language. Finally, from the theoretical linguistic point of view, we want to ensure that our theories about the human language faculty are grounded in data from as wide a range of languages as possible. We want to know what a possible human language is, so it's important to us to study the fading ones while we still have a chance. But there's a problem. Fieldwork is hard. Not only does it require linguistic aptitude and expertise, it also requires a good deal of social intelligence and interpersonal skills. I'll venture to guess that this is a rare combination. Not only do you need to be well versed in the theory or analysis that you're exploring, you need to be able to empathize with the language consultant and be able to understand the information she is giving you, and be ready to use that information in order to formulate the next relevant question, furnished with a well thought out context. It is definitely a challenging task for both field worker and consultant. As if this were not hard enough, adding the endangered languages aspect into the mix makes it even harder. Because now the field worker must contend with balancing the requirements for academic success with the expectations of the speaker and the language community, who tend to be more concerned with documentation and revitalization. And of course, there is the issue of data scarcity. Once your 1 or 2 hours of weekly elicitation time are over, there's very little you can do to answer that burning question that occurred to you after you were able to process all of the information that your consultant gave you. The point I want to make here is that the first two sources of difficulty will always be with us. Linguistic fieldwork will always be challenging. However, we can do something to deal with the difficulties that result from resource scarcity and the balancing of conflicting requirements. We can use tools that allow us to share and reuse data so that more data are available, and so that non-academic interests can more easily be served by those data. Having defined fieldwork as the generation of artifacts, we can identify two broad types of fieldwork artifact: primary data and higher level artifacts. Here is an example of primary data from my own fieldwork on Okanagan. We have transcriptions, translations, morphological analyses, morphemes, audio recordings and video recordings too, images, perhaps used as stimuli in experiments or as aids in representing contexts, metadata, that is, who created the data, when was it elicited, and analytical representations, such as this phrase structure analysis of an Okanagan determiner phrase. By higher level artifacts, I'm referring to things like descriptive grammars, dictionaries, pedagogical materials, and research papers. But we could also include here language learning software and texts representing stories and narratives. The green boxes in this slide are meant to represent the primary fieldwork data that underlie all of these higher level artifacts. Now this is what happens when a linguist fieldworker is writing a research paper. We will draw on our own fieldwork data, but we will also draw on information from descriptive grammars, dictionaries, and pedagogical materials. However, it would also be highly useful to be able to draw upon the unpublished primary data that underlie these higher level artifacts. This type of data flow, the type that ought to be happening but doesn't really happen, is indicated by the red arrows. Analogously, a fieldworker writing a grammar will draw on the published sources of her fellow fieldworkers, but would also benefit from easy access to the primary fieldwork data that underlie those higher level artifacts. And the same can be said for the educator fieldworker. Now this slide represents what tends to happen by default. Fieldworkers may, on occasion, request access to the data stores and field notes of their peers. But for a number of reasons, this rarely works out well. It's hard to find time to distribute your primary data, and you have to petition a bunch of different people, and the data are always in a state of flux. Different fieldworkers use different formatting conventions, etc. So one of the major goals of LingSync is to facilitate this data sharing. If fieldworkers could all contribute to a centralized database that helped them with their tasks, and which also made their data accessible and useful to their peers, the whole system should run more smoothly for everyone. Now some might wonder whether data sharing is really going to have much of an impact, especially from the theoretical linguist's point of view, where we associate fieldwork with asking very particular questions about esoteric constructions. It might seem like only our own fieldwork data will be of much use. However, I think that this data sharing is beneficial, and the reason for this is the fact that the data are so scarce. This quote summarizes the state of the indigenous languages of British Columbia, but the same generalization holds all over North America and elsewhere. Many of the languages that we study have very few speakers, hundreds, dozens, or even fewer. And the data are scarce. There is very little written or audio recorded data, and in fact, in some contexts, the fieldwork performed by academics and/or communities generates the majority of the data on these languages. So here is the vision that LingSync seeks to realize. Imagine you had easy and unified access to your own fieldwork data and the data of your peers, including crucially the unpublished data that underlie the higher level artifacts just discussed. Again, LingSync is designed so that descriptive linguists writing grammars and dictionaries, developers programming language learning software, teachers developing language learning materials, and theoretical linguists seeking to advance linguistic science can share their data and collaborate to their mutual advantage. LingSync allows multiple users to contribute simultaneously to a shared access corpus. The software is open source. Besides the obvious benefit of being free of cost, this means that its inner workings are easily inspected. It can be improved or altered by others, or parts of it can be used in other software, and its life is not tied to a particular organization or individual. In order to make data sharing truly possible, it's important that the software work on all major computing platforms, so that fieldworkers are not left out of the loop by technical circumstance. Since LingSync is a web application and runs in a web browser, this is not an issue. LingSync is also a web service with a consistent API. This means that its data and functionality are highly reusable, for example, by other applications such as a language learning tool or an online dictionary tool, or for export, etc. Also, it has features which allow users to control who has access to which data. I will expand on these last 2 points. This slide compares a traditional web application to a web service. LingSync is a web service with a number of different GUIs, graphical user interfaces. The crucial difference to notice here is that the web application communicates via a complicated jumble of content formatting and application logic. A web service like LingSync, in contrast, communicates in an easy-to-understand way and deals purely in structured content. The high-level insight is simply that this architecture makes LingSync highly reusable. Now I'll give you an overview of how LingSync works. Using LingSync, a fieldworker can create a corpus to house their data. Then other fieldworkers can create corpora for their data. A fieldworker may then grant access at various levels to his or her corpus. For example, she may grant read-only access to certain users, administrator access to others, and no access to everyone else. A fieldworker may also specify that her LingSync corpus be made public, so everyone can see it. It is also possible, via the other main LingSync interface, to encrypt parts of your data, for when more fine-grained privacy is needed. LingSync also has version control, so whenever a change is made, previous state is saved. This means that changes can be undone, if necessary. By allowing such fine-grained control over access, and by implementing version control, LingSync balances the need for collaboration, data sharing, and data reuse, with the requirement, whether it be from speakers, language communities, or fieldworkers, that some or all of the data be kept private. Of course, a given user may also have more than one corpus, used for different purposes or languages, and with different permission settings. Another way of understanding LingSync is as a hierarchical tree structure. A user can create any number of corpora. The creator of a corpus is automatically an administrator of that corpus. An administrator can grant other users access to a corpus under his administration. The data in each corpus are divided into sessions. Every piece of data belongs to one and only one session. A session is meant to represent an elicitation session. For a session, one can specify metadata like goal, consultants, language, dialect, and date elicited. Having discussed why LingSync was created, and having described it abstractly, I'm now going to show you how to actually use it. Before I begin showing how to use LingSync, I want to make it clear that what I am showing you here is one graphical user interface to your LingSync data. The GUI that we are going to learn is called LingSync Spreadsheet. It's easy to use. The LingSync Chrome app was developed first. It has more features. It has better import-export. You can work offline and then sync your data when you connect to the internet, and it allows users more flexibility in defining their data structures. However, it is more complex and arguably more difficult to learn. It is important to realize, though, that you can use either the spreadsheet or Chrome app interfaces to work with the same data. The Dative GUI is what I'm currently working on. The plan is to have Dative as a viable alternative to spreadsheet in the near future. It will consolidate the best properties of the Chrome app, spreadsheet, and the OLD into one interface. More on that later. For now, we'll focus on the spreadsheet GUI. It's a web application, which means you don't need to download anything to use it. Just point your browser to app.lingsync.org. Now, you can follow along if you want or not. A little bit later, I will walk everyone through registration and data entry. For the moment, I'm just giving you an illustrated overview of the system. If you already have an account, you can select the LingSync server and log in. If you don't have one, you can register in the top right and follow the steps to get an account. This is one of the nice features of LingSync. You can get started using it right away, without downloading anything and without waiting for a human to approve your registration. Remember LingSync's hierarchical data structure. Access to data is controlled at the corpus level. Once you've logged in, you'll see the list of corpora that you have access to. These are the ones that I have access to. Yours will probably look something like this. You can click on a corpus to begin using it. Alternatively, you could click on Corpus under the Settings menu and then create a new corpus, as shown here. And you can always click on the LingSync icon on the top left to get back to your corpus list. Once you have clicked on a corpus, the interface for choosing an existing session or creating a new session will be revealed. Here is the interface for creating a new session. We see fields for goal, consultants, language, dialect, and data listed. So once you have activated a session, we will be brought to the data entry interface, shown here. Now, LingSync has a feature called the semi-auto glosser, which learns how you segment words into morphemes and how you gloss those morphemes. The semi-auto glosser attempts to guess the analyses of your words as you enter them. While this can be a useful tool to speed up data entry, it is a good idea to turn it off until you have more data in your corpus for the glosser to learn from. To turn it off, simply uncheck the box for semi-auto glosser on the navigation bar. You can turn it back on at any time. If you click on Session in the navigation bar, the system will reveal the interface for changing to a different session, editing the metadata of a session, deleting a session, or creating a new session. Once you're in the data entry interface, you can create a new record by clicking on an input field and typing in the appropriate data. You can then hit the Enter key or click Create New. To move between records, click or use the up and down arrows. As you enter new records, make sure you click the Save button to save them to the LingSync database on the server. You won't be allowed to navigate away from the data entry interface with unsaved records. The application will autosave every 5 minutes. To edit an existing record, just click on it. To delete a record and do other things, click on the little icon in its bottom right to bring up more options. Click Delete this record to delete it. You can also add comments and upload audio files. The record is the basic unit of data in LingSync. The default interface provides the fields shown here. The first 4 should be familiar from the interlinear gloss text convention. The utterance field should contain a transcription in the object language. The morphemes field is the utterance segmented into morphemes. The gloss field is isomorphic to the morphemes field and contains a gloss for each morpheme. The translation field is for a translation of the whole utterance in the metalanguage, for example, in English or Spanish. The judgment field is for indicating the grammaticality or oddity of the object language form. Tags can be used to organize and categorize records. For example, by tagging records that contain an incorporated noun as NI, we can search for this tag later and get a set of relevant records. The spreadsheet GUI offers basic search and export features. To search, type in your search terms and click Go or press Enter. This is substring match in any field. Make sure you are in the session you want to search. You can search an entire corpus by selecting all sessions in the session interface. To filter your results further, type in a new search term. This will search only the results of your previous search. To make a brand new search of all the records, just click Clear Results. Export is performed within the search interface. Click the checkbox next to each record that you want to include in the export, or click on the Select All button. Then click Export. Here is what an export looks like. You can copy and paste this into another application. You can also export your data from the Frequently Asked Questions page. Click on CSV to export as comma-separated values, or click on JSON to export as JavaScript object notation. This is what a JSON export looks like. JSON is a data structure that can be parsed by any modern programming language. If you click on User Interface under the Settings item in the navigation bar, you can choose a template, which determines which fields are available for your records. A number of different data entry templates are available. If you activate a different template, and the data entry interface doesn't immediately change to reflect that, then just log out and log back in to refresh the interface. If you click on Corpus under the Settings item in the navigation bar, you will see the interface for creating a new corpus and adding users to the corpus you're currently using. Right now, as this slide shows, I am the only administrator and reader of my Blackfoot corpus. Nemo33 and I are the only writers. I can easily add other users with administrator, reader, or writer privileges. Once you start typing a username in the Add User field, the app will auto-suggest matches from the list of existing usernames. Here I have granted the user Gretchen M read-write access to my Blackfoot corpus. Click on the Frequently Asked Questions item in the navigation bar to get to the Frequently Asked Questions page. Here you will find answers to some questions and links to more documentation. LingSync has a Facebook page for news and updates, a series of video how-tos organized into a playlist on YouTube, and its source code, issues, and milestones are all available on GitHub. If you are a developer and interested in contributing to or hacking LingSync, this is where you'll want to go. But all you have to remember is the URL for the main LingSync website, www.lingsync.org. The Facebook, YouTube, and GitHub pages are all linked to from this site. This site also contains other resources, such as the tutorial, which is the set of slides similar to the ones I'm showing you now. You can email us at info@lingsync.org with questions, comments, bug reports, feature requests, etc. That email address is also available under the Contact Us link of the main website, as shown here. So now we're going to shift gears a little bit and talk about the future of LingSync, before moving on to some hands-on practice working with the LingSync spreadsheet app that I just showed you. Specifically, what I'm going to show you are the interesting features of the LingSync Chrome app and the OLD. In particular, the morphological parser creator application of the OLD and the results of my experiment in using it to create parsers for Blackfoot. These are the features that you can expect to see in the new soon-to-be-released LingSync GUI. At the end, I will give a quick preview of this new GUI, which I've dubbed Dative. The LingSync Chrome app, also called the LingSync Prototype, is a Chrome application. This means it runs only in the Google Chrome web browser. You can download it for free from the Chrome Web Store. One of the benefits of being a Chrome app is that it was, as a result, easier to make this LingSync GUI work offline. So the LingSync Chrome app works offline, and when internet connectivity is restored, your locally stored data are synced with the server-side database. The LingSync Chrome app also has superior import and export functionality compared to the spreadsheet GUI. This is important because it allows users to easily get their data in and out of LingSync for a variety of different purposes. Good import-export support also makes it easier for field workers to use LingSync and other tools, such as Flex, Elan, and Toolbox, in a complementary manner. The LingSync Chrome app also has a more customizable data structure. In contrast to the predefined field templates of the spreadsheet GUI discussed previously, the Chrome app allows users to define whatever fields they want. The Chrome app also has the encryption features alluded to previously. That is, it allows for more fine-grained control over who has access to which data, which is useful in certain fieldwork contexts. The new Dative LingSync GUI will add support for these features, most urgently, import and export. Now we'll discuss some of the more interesting features of the Online Linguistic Database, or OLD, that will be incorporated into the new LingSync Dative GUI. Here is a screenshot of the Blackfoot OLD. This is a web application that has been used for the past 6 years or so by a number of fieldworkers and researchers to collaboratively document and study Blackfoot. This screenshot shows the beginning of a representation of one of my elicitation sessions. Whereas LingSync, as we have seen, is a set of user-created corpora where creator admins can grant access to other users, the OLD is software that is used to create completely independent language-specific web applications. This slide schematizes 8 language-specific OLD applications. These are listed with their URLs and names, both of which are based on the ISO 639-3 code of the relevant languages. This basic difference in structures between LingSync and the OLD has ramifications. When developing the OLD, I was relatively more concerned with data sharing and creating consistent data sets. In contrast, the original LingSync development vision, though it valued collaboration and data sharing, put a relatively greater emphasis on data privacy and fine-grained control over access to data. Basically, in an OLD application like the Blackfoot OLD, everyone has access to everyone else's data. As a result, I have worked hard at building features that promote consistency and which make the data accessible and searchable. These are some of the major requirements that I have for a fieldwork application. I want it to help me to create data that are consistently structured and formatted. I also want it to assist me in creating higher-level artifacts for my primary data, for example, research papers. I also want it to help me to get the data that I need with speed and precision. Some salient OLD features that respond to these requirements are listed here. Morpheme cross-referencing and configurable validation promote the creation of consistent data. The general-purpose text creation feature allows for the creation of higher-level artifacts like research papers right within the software. And the search features help us to quickly get precisely the data we need. This slide illustrates the OLD's morpheme cross-referencing feature. When you enter a morphologically complex form, the OLD displays the morphemes as color-coded links to the lexical forms that already exist in the database. This provides immediate visual feedback on the lexical consistency of your morphological analysis. In short, the blue links indicate perfect matches, the green links indicate partial matches, and the absence of a link indicates that the morpheme shape or gloss matches no morpheme in the database. This slide illustrates another consistency supporting feature of the OLD, input validation. Users can specify inventories of symbols that can be used to constrain the types of inputs that are permitted in particular fields. This can help to ensure that the orthographic, phonetic, and/or phonemic transcriptions have a base level of consistency. A related feature is orthography conversion. A user can choose an interaction orthography. The OLD will transparently convert inputs to and outputs from a designated storage orthography for consistent storage in the database. This is useful for endangered languages fieldwork contexts where it is not uncommon for multiple orthographic conventions to coexist. The OLD allows for the creation of texts. An OLD text is an ordered list of references to forms in the database. The text can then be exported as a LaTeX document, which can then be used to generate a PDF. An OLD text can also contain prose and markup for formatting and example cross-referencing. Texts themselves can be associated to audio, video, or image files. The OLD has powerful search functionality. An OLD search is an arbitrarily complex tree structure with Boolean operators as the non-terminal nodes and filter expressions as the terminals. The search expression at the top requests all forms that are sentences, and are not ungrammatical, and either contain the morpheme shape wa or contain approximate-like gloss. As indicated here, OLD searches can use regular expressions. The OLD also allows users to search for forms that contain specific morphemes. Imagine that we want to retrieve all forms that contain just morpheme 1, but our database also contains morphemes 2 and 3. Morpheme 2 has the same shape as morpheme 1, and morpheme 3 has the same gloss as morpheme 1. But notice the shape gloss category field in the bottom rows of all of these tables. This is automatically generated by serializing the values of the fields in the first 3 rows. The shape gloss category is essentially a unique signature for each morpheme. Now, if we use a regular expression to match the shape wa in the morpheme shape field, we will get forms that contain either morpheme 1 or morpheme 2. If we try to improve this by matching wa in the morpheme shape field and prox in the gloss field, then we will get all forms that contain morpheme 1, which is what we want. But we will also get any forms that contain both morpheme 2 and morpheme 3, which is not what we want. The solution is to search for wa followed by prox in the shape gloss category field. Only this search will give us all and only the forms that contain morpheme 1. The OLD also allows for structural searches using tgrep2. That is, it allows you to search for phrase structure patterns. While this is particularly useful for linguists interested in syntactic phenomena, it does require that phrase structure representations be already present in the database. So now I'll talk about the morphological parser creator functionality that I've built into the OLD and that I will be incorporating into LingSync in the immediate future. I hope this will be interesting to the present audience, both because it's an interesting and useful tool for linguistic fieldwork, and because it relates to lexical, morphological, and phonological analyses of Blackfoot, a language that some people in the audience can do fieldwork on. There are 2 big features that I want to see in a fieldwork application. I want to be able to automate the task of creating morphological analyses. I also would like the system to help me in evaluating my analyses. This is what I mean by automating the parsing task. I want to be able to type in my transcription and have the system automatically generate for me the morphological analysis in IGT format. While hand parsing words is useful practice when one needs to develop proficiency with the morphology of a new language, this task soon becomes tedious. However, morphological parsers contain useful information, especially when it comes to performing targeted searches, as we have seen. This automation could save significant fieldworker time that could be better spent on other higher-level fieldwork tasks. On the other hand, if I decide to manually enter a morphological analysis, I would like the system to be able to notify me if what I've entered is not predicted by the models that I have specified. More generally, I want the system to be able to run through all of my data and show me the forms that are not predicted by my models. This would be an objective and speedy measure of the observational adequacy of a model. It could help us to build better ones. So I built an application for creating morphological parsers, integrated it into the OLD fieldwork tool, and then I tested this application on Blackfoot. At the highest level of abstraction, a morphological parser is a function that takes surface transcriptions as input and returns morphological analyses as output. This schematic shows the components of a morphological parser. The morphophonology component returns a set of possible morphological analyses. Because natural language is full of ambiguity, a single surface transcription may correspond to multiple morphological analyses. The job of the candidate ranker, represented by the green box, is to transform the unordered set of candidates into a list of candidates ordered according to their probability, given a corpus of expertly analyzed words. In terms of implementation, the morphophonology is a finite state transducer, while the ranker is an n-gram language model. I will say more about these terms shortly. In terms of their specification, the lexicon, morphotactics, and ranker are all automatically extracted from corpora that a user creates for these purposes. The phonology, however, must be specified by the user as ordered phonological rules. The good news is that as linguists we already know how to do this. Clever computational linguists and developers have already created tools to convert our ordered phonological rules into computer programs that efficiently translate surface representations to underlying ones and back again. Here we see a toy morphophonology which can only parse one word, namely Blackfoot nitspie, meaning I danced. The phonology is a pair of ordered rules. The morphology is represented here as a context-free grammar. And here we see a network diagram representation of a finite state transducer that encodes the Blackfoot phonological rule breaking, which is called breaking. An important property of finite state transducers is that they are symmetrical. Even though they are specified using a generative notation, they can be used for both generation and parsing. So the take-home message here is that your rule-based phonology is a computer program for a generator and a parser, or at least a good first draft of such a program. Jumping ahead a little bit, the phonological rules of Donald France's Blackfoot grammar are essentially a computer program for building a computational model of the phonology of this language. This slide attempts to briefly explain what an n-gram language model is. An n-gram language model is a data structure that can be used to assign a probability to an arbitrary sequence of elements based on counts of previously seen length n subsequences. Basically, if we have a corpus of morphologically analyzed words, we can use that corpus to build an n-gram language model to estimate the probabilities of potentially never-before-seen analyses and rank them. So, the morphological parser creator is essentially a function that takes rewrite rules and corpora as input and returns a morphological parser as output. The good news is that collaborative fieldwork software can facilitate the creation of the required corpora. And the test-driven phonology development feature of the parser creator can help us to build phonologies as ordered rewrite rules. I will elaborate on these 2 points in a moment. This diagram shows how I created the Blackfoot morphological parser. An overriding guiding principle was to conform to existing conventions of Blackfoot scholarship. I implemented as faithfully as possible the phonology of France's grammar, including the allomorphic generalizations. The bulk of the lexicon is the dictionary of France and Russell. I used the morphologically analyzed words of the Blackfoot OLD and the grammar to extract morphotactics and the n-grams. I assumed the standard orthographic conventions of the language, which is to say that the parser analyzes orthographic transcriptions. Finally, I evaluated the parser against the morphologically analyzed words of the Blackfoot OLD. The net effect is that I am treating the grammar and the dictionary together as a theory of the morphophonology of Blackfoot. I am testing that theory. We can consider France and Russell's dictionary plus the Blackfoot OLD plus France's grammar as one big dataset. This is the Blackfoot dataset that was used to build and evaluate the parsers. This slide shows where the data come from. About 7,500 forms are from original fieldwork. About 1,000 are the example words and sentences from the grammar. About 500 are from other textual sources like Taylor's grammar or Uhlenbeck's texts. About 15,000 are the morphemes and example words and sentences from the dictionary. From this dataset, I extracted a corpus of morphemes for building the lexicon of the parser, as well as a corpus of morphologically well-analyzed words for building the morphotactic rules, the n-gram candidate ranker, and for evaluating the performance of the parser. I will discuss these corpora presently, but first I begin by reviewing the phonology. I built the Blackfoot phonology using the general phonological rules and allomorphic alternations of the grammar. Here is the T-affrication phonological rule. I have changed the rule trivially so that it transforms the hyphen delimiter. The important point is that the FST rule syntax is so similar to the context-sensitive format of the source that the mapping is trivial. The breaking rule illustrates a complication. The rule references breaking I, the capital I. However, the dictionary does not use breaking I. Breaking I causes a preceding velar stop to post-sibilate, whereas normal I does not. My solution is to optionally break the velar stop before high front vowels. The optionality is indicated by the parentheses around the arrow. Obviously, this optionality is undesirable, since it predicts ungrammatical surface forms like nita kipi. The better approach would be to make application of the breaking rule dependent on the lexical contexts that are implicit in the dictionary. But that's tedious work, and I just haven't had time to do it yet. Blackfoot has a lot of allomorphy, especially at the left edge. This slide shows how the first syllable of certain morphemes is transformed into a mid-back rounded vowel in certain contexts. The dictionary does not exhaustively list these allomorphs. I handle them in the phonology as lexically conditioned transformations. In this rule, we see I becoming O, but only when it is the I at the beginning of the word imita, dog. This is an extremely domain-specific transformation, since it is restricted to a single lexical item. So-called 3mm allomorphy has a more general domain of application. 3mm refers to certain verbs that are suffixed by long m only when third-person agreement is present. In this rule, the green font shows the first 8 of the 45 or so 3mm verbs identified. The orange font shows the agreement suffixes. Particularly troublesome for the current task is the so-called initial change in Blackfoot, which correlates with past tense interpretations. The verb oxkatsi sometimes participates in initial change and sometimes not, yet the interpretation appears to be the same. This would appear to support the optionality in the rule that I ultimately used to implement this. However, at the bottom we see two nearly identical verbs, one of which participates in this initial change phenomenon and one of which does not. The parser creator helps in the creation of a phonology by allowing you to write tests that the phonology should pass, and then automating the task of determining how many tests pass and which ones fail. I call this test-driven phonology development, since it is analogous to test-driven development in the software world. Software quickly becomes too complex for mere humans to anticipate how changes to one component will affect all of the others. I think this reasoning applies equally well to the building of grammatical models. With test-driven phonology, we can immediately see if our changes are causing bugs, and whether our test scores are improving. Here we see a bunch of comments in my Blackfoot phonology script, which are test declarations. These tests are simply the illustrative examples taken straight from France's grammar. The morphological parser creator runs the tests against the phonology and reports which ones fail. This way, you can tweak the phonology until you get the success rate you want. Here is the ordering that I came up with for the phonological rules of France's Blackfoot grammar. France does not explicitly specify an ordering, so this ordering, along with my specific formulation of the rules, is a small contribution to the phonological analysis of the language. This ordering causes all 127 specified tests to pass. The parser creator's test-driven development functionality facilitated the discovery of this ordering. One thing to note is that the phonology is considered to have passed a test even if it overgenerates. That is, even if it maps a given underlying representation to more surface representations than just the correct one. Because of the optionality in some of the rules just described, this phonology does overgenerate. However, from a parsing perspective, this is okay, because so long as the correct analysis is returned for a given surface transcription, the morphology, and failing that, the analysis ranker, will filter out the incorrect analyses. This slide summarizes the phonology. All told, the phonology consists of 42 ordered rules. 18 of these rules are lexically conditioned and capture allomorphy. The other 24 are general phonological rules and correspond as faithfully as possible to the phonology of the grammar, although, as just described, optional transformations were used. And again, the phonology passes all 127 tests specified. And since a phonology is a computer program, my Blackfoot phonologies are all open source scripts that are version controlled and available on GitHub. The lexicon of the parser was taken primarily from the dictionary. The dictionary formatting is consistent enough that it was relatively easy to extract shape, gloss, and category information. In total, the lexicon consists of some 5,100 morphemes. Almost all were taken directly from the dictionary with their original categories. This slide shows the 28 morpheme categories and the number of morphemes in each category. The dictionary does not list inflectional affixes, highlighted in red here. I created the inflectional categories Agreement A and Agreement B for the inflectional prefixes and suffixes respectively. Some of the other categories were also created by me or other contributors to the dataset. For example, the tense, aspect, and modal categories highlighted in green, and which are drawn from the dictionary's adjunct category. The resulting lexicon can be viewed as a simple context-free grammar, where categories are non-terminal nodes that expand to sets of morphemes. The morphotactic rules were extracted from a corpus of words in the Blackfoot dataset. The parser creator first discovers all of the well-analyzed words in the corpus. A well-analyzed word is one where all of the morphemes in the analysis can be identified. From the categories of these identified morphemes, the OLD fieldwork software generates category strings for well-analyzed words, as shown in red here. Based on this, the parser creator concludes that any sequence of morphemes with the same category signature is a grammatical word. All told, some 6,600 well-analyzed word tokens were identified in the Blackfoot dataset. These correspond to 940 distinct morphotactic rules. This slide shows the 20 most common morpheme category sequences. Here is a representation of the entire morphology as a context-free grammar. Notice that this morphology overgenerates. For example, it will incorrectly predict the grammaticality of an animate noun with an inanimate plural suffix. For example, imitasts. Once again, from a practical parsing perspective, this is not a major issue. However, when it comes time to use the computational implementation to automate testing of the underlying model, this will become an issue. In future work, I will improve the morphology so that it can handle these dependencies, either via a more fine-grained categorization of morphemes or via a finite state device known as flag diacritics. From the 6,600 well-analyzed word tokens, I identified 3,245 gold standard analyzed words. These are words with a single identifiable correct analysis. I used these to train the language models and test the fully assembled parser. When evaluating a language model, it is important to train the model on one dataset and then test it on another. Otherwise, you are just testing the model on data it has seen before and are not really assessing its predictive power. I repeated the following process 5 times and then averaged the results. I randomly divided the gold standard analyzed words into a 3,000 word training set and a 300 word test set. I used trigrams with a particular widely used smoothing algorithm. The models were trained on corpora that contain only about 6,000 trigrams, which is quite a small number as far as language model estimation is concerned, but I had to work with what was available. This slide shows the 20 most frequent trigrams in one of the corpora used to train the language model. Most of these are agreement morphemes at word boundaries. Here are the results. The parser got exactly the right answer 14% of the time. It has an F-score of 0.32, with a perfect score being 1. An F-score is a standard metric for parser evaluation. It is more fine-grained than simple parse accuracy. An F-score is a function of precision and recall. Imagine that the morphological parsing task is to guess all of the morphemes in a word, regardless of order. Precision is the percentage of our guesses that are correct. Recall is the percentage of the correct answers that we got. The parser does relatively well on precision. When it guesses a morpheme, it is a correct one about half the time. It does less well on recall. It's only guessing about a quarter of the correct morphemes. In the context of a fieldwork application, where a major goal is to expedite the creation of morphological analyses, the F-score is arguably more important than the overall parse success rate. Even if the parser can't always give us exactly the right answer, it can at least give us an answer that is partially or mostly correct. It should take less time to repair a mostly correct answer than to type out the correct one from scratch. Consider that the phonology is only 21% accurate. This is an upper bound on the success of the parser as a whole. The parser can do no better than 21% until the phonology improves. The language model does pretty well. When the correct parse is in the set of candidates, the language model can identify it 72% of the time. By inspecting the failures of the phonology, we can see that 28% are due to unpredicted pitch accent marking, and that many others are due to changes in the length of phonemes. The first table shows an example where non-lexical accent is introduced. The grammar does not account for this phenomenon. The second table shows an example where two underlyingly long vowels surface as short. My provisional strategy for improving the performance of the phonology was to obliterate all accent marking and length distinctions. The no accented vowels rule transforms accented vowels to their unaccented counterparts. Similarly, the shorten rule transforms any contiguous sequence of two or more characters to one of those characters. These rules were added to the end of the phonology after all of the other rules. In addition to modifying the phonology in this way, it was also necessary to remove length and accenting distinctions to orthographic inputs prior to parsing. The phonology has now improved dramatically from 21% to 60%. However, the overall performance of this second parser is more modest, a 3% jump to 17%. The F-score has moved up from 0.32 to 0.4. Observe that the language model, which has not changed, now performs much more poorly. What has happened is that the phonology now generates the same surface form for so many underlying forms that the language model must rank a significantly larger number of candidates. In fact, the morphophonology of parser 2 now generates on average 1,800 analyses per input. Contrast this with the morphophonology of parser 1, which generated fewer than 10 analyses per input. Here are my conclusions. First, I assert that I have created a Blackfoot parser that will be useful to field workers. Secondly, I have meticulously uncovered the gaps in the analyses of the grammar and the dictionary. Finally, I have built a tool which can help in building additional parsers and models that can be used to expedite data creation and automate the testing of analyses. I will briefly unpack each of these conclusions in turn. The parsers built and reviewed here are effective tools that can help Blackfoot fieldworkers to generate morphological analyses more quickly. I maintain this assertion despite the relatively modest 17% overall parse success rate. Another statistic is relevant here. The parser is able to suggest an analysis for 88% of the words it sees. This, combined with the F-score and recall scores of 0.4, means that 88% of the time the parser will suggest 40% of the correct morphemes. Also consider that the morphophonology is 60% successful. The fully correct analysis is among the candidate set 60% of the time. Once this parser is incorporated into a graphical user interface for data entry, which suggests analyses ordered by probability, an interface where the user can click and choose the analysis that is most correct, it is clear that this tool will help users to more quickly generate morphological analyses. Since researchers often do not even take the time to create morphological analyses, if we can make it easy for them to simply select the best suggestion of the parser, perhaps for later refinement, then more useful data will be created, and the effectiveness of morphological search will be increased. And of course, there is a bootstrapping effect here. As more morphological analyses are entered and hand-edited, the language model can be re-estimated, and the performance of the parser will improve in turn. We already know that there is still work to be done on the morphology and phonology of Blackfoot, but a benefit of the current approach is that it offers a fully explicit computational model of the entire morphophonological system, and shows us what exactly needs to be done to improve it, and how we can objectively measure such improvements. One particularly glaring gap is that we don't have a model that exhaustively accounts for the allomorphy that is described in the grammar, and which is implicit in the dictionary. Sifting through the dictionary and incorporating this allomorphy into the types of models described here is not glamorous work, but it will result in better parsers and in more accurate models. This brings us to pitch accent, and in particular the problem of predicting the location of accent marking. Recent work by Weber 2013, Weber and Allen 2012, and earlier Kaneko 1999, has uncovered generalizations that predict where non-lexical pitch accent occurs, depending on the category of the word, the number of syllables it has, and the location of any lexically specified accent. These generalizations depend on the syllabification work of Denzer King 2009 and Derrick 2006. I have already begun implementing phonological rules which perform the syllabification, and which introduce non-lexical pitch accent in the correct places, in accordance with these generalizations. It is definitely possible within the finite state framework used here, and its incorporation into these Blackfoot parsers will result in a significant reduction in the size of the candidate analysis set returned by the current morphophonologies, thereby reducing the burden on the poor candidate ranker. One thing that I have not had time to talk about is the issue of variation in the standard Blackfoot orthography. This variation is due to a number of factors: vagueness in the spelling rules, cross-dialect and cross-speaker pronunciation differences, linguists using the orthography to represent extra phonetic detail, like devoiced word final vowels. Part of the solution is to allow for separate phonetic transcriptions in the data, and build dialect and speaker-specific phonologies that parse these phonetic transcriptions. The computational models shown here can also be the starting point for prescriptive spelling rules in order to work towards standardizing the orthographic conventions. However, it may be necessary to build distinct orthographic models for different dialect communities. Finally, as mentioned above, the Parser Creator application, integrated as it is into a collaboratively contributed fieldwork database, can help fieldworkers to build parsers and computational models using data they already have and phonologies that have already been written. In addition, the Parser Creator can help to build an accurate phonology by allowing us to specify tests and then automating the testing of a transducer. This is what I plan to do next. I want to create graphical user interfaces, or GUIs, that suggest ranked IGT morphological analyses to fieldworkers while they are entering their data. I need to create a GUI for the Parser Creator. This will automatically evaluate the parser and its components against specified datasets so that fieldworkers can improve their models within a user-friendly environment. I need to improve the Blackfoot models in the ways I've alluded to. My Blackfoot morphology is currently highly inaccurate. Refining it by simply adding morphological dependency restrictions will improve the performance of the parser. I also need to incorporate the non-lexical pitch accent generalizations into the phonology. Finally, I need to do the grunt work of identifying the lexical classes that participate in particular allomorphic alternations. And after that, I'd like to use the Parser Creator tool to build parsers and grammatical models for other Algonquian or First Nations American Indian languages. Speaking of the new Dative GUI, here is a screenshot of browsing records or forms of the Blackfoot OLD through the Dative interface. Here again, we see the Dative GUI, this time with a different color scheme. This is showing us the interface for entering a new record. So here is a summary of where I want to go. Import, export, text creation, better search, morphological parser creator. Okay. Now we have come to the hands-on portion of the tutorial. We are going to collaboratively populate a LingSync corpus with Blackfoot data from one of my elicitations. I'll begin by handing out these pieces of paper, each of which contain a Blackfoot word or sentence with IGT analyses, which should be entered into the corpus as a record. While these are going around, I will put up some slides to remind you how to register for a LingSync account. First thing, let's go to app.lingsync.org. Click on Register in the top right. Choose LingSync as your server, then enter a username, a password, repeat the password, confirm your email address, and then click Register. Now the system should have brought you to the login page. Again, choose LingSync as the server and enter your username and password, and then click Login. Now I have to give you all access to the Blackfoot U Calgary workshop corpus that I have already created. So you will need to tell me your usernames one by one. Once I have added you, you should be able to click on the LingSync icon in the top left to access the list of corpora that you have access to. Then you can click on the Blackfoot U Calgary Workshop Corpus, which will bring you to the list of sessions within that corpus. And you should select the one labeled 9/11/2014, being hot, cold, and ... and click Go. Now you should see something like this, and you can begin entering your records using the slips of paper that have been handed around. I will be walking around to answer any questions or to help out. Thank you. Nitsukutachsitak.